So we're considering the strain energy theory. Now, the strain energy theory is yet another theory of failure that we use for analysis because we want to analyze when failure is likely to occur. Previously, we had used other theories. So this is just yet another analysis theory that is very useful. Now let's see what is involved in this. As usual, we'll start with the definitions and also then we put in the factors that are involved in here. So in this case, we're saying that the strain energy theory states that failure of a material will occur only when the strain energy in that material reaches the total strain energy of the material at the elastic limit, and we're considering simple tension. In other words, we're saying that a material can fail if the amount of strain energy it's going to have is equal to that strain energy that it has when it reaches the elastic limit or when it is at the elastic limit for a material that is being loaded in simple tension. That is what this one states. Now, in this analysis, you've noticed that we've been talking about three stresses, taking us to a three-dimensional stress system. So therefore, in this case, we use this standard expression where U represents the energy. Then U, therefore, is equal to 1 over 2E. The E is the Young's modulus. Then inside the brackets, you have stress number 1 squared plus stress number 2 squared plus the third stress squared minus 2 over M. Then in the brackets, you have stress 1, stress 2, stress 2, stress 3, and this one should be stress 1, stress 3. I think this was just a typo error. Stress 1, stress 3. So this combination is what we get for a three-dimensional stress system. What you are seeing there as M is actually supposed to be like, when you isolate it, it should be 1 over M as a constant. The rest are the stresses. Stress 1 is the positive one. Stress 3 is the compressive one. But because we are squaring these numbers in this case here, the negative disappears for the third one. Then in between, we always have zeros. Now, in this case, we are saying that we only take absolute values for the three stresses. Now, if this is the case, when we say we only take absolute values, it means we can now pick the strain energy first of all. Remember that strain energy per unit volume was stress at elastic limit squared over 2E. So this is now at the point of failure. We're saying that a material will fail when the amount of energy, the amount of strain energy it reaches is equal to that at elastic limit. So this is what you have here. Stress squared over 2E. Stress E, it's trying to tell us that this is the stress at elastic limit. Then you can notice already that here I have this 2E, which is also there. So this can cancel. Having cancelled, then we remain with what is in the brackets. Since it's only one which will be remaining outside the brackets, then we can as well open these brackets, the square brackets. So we have stress 1 squared plus stress 2 squared plus stress 3 squared minus the same 2 over M. Then in the brackets, we have stress 1, stress 2 plus stress 2, stress 3, and then plus stress 1, stress 3 is equal to stress at elastic limit squared. Then continuing, here we're saying that during the design process, where we put that this is stress at elastic limit, you replace it by the stress, what you are calling the working stress. Additionally, there is no stress in the Z plane, the third one. So this tells us that in a two-dimensional stress system, stress number 3 is out. You just remain with 1 and 2, meaning stress number 3 is 0. With that being the case, we put back in the equation, therefore we have stress 1 squared plus stress 2 squared minus 2 over m. The stress 1, stress 2 is equal to this. This is the one we were saying it can even become stress T, or just stress being the working stress. And of course, this is what we're talking about here, where we substitute this by the working stress, which can be either less than or equal to that stress there we are referring to. This, of course, is trying to refer to a point where we're now trying to do the analysis in a design process. We want to get to the working stress. And our idea is to analyze that failure and see when things may go wrong. Now, what factors do we need to note when we're applying the strain energy theory? Number one is that these results that we're talking about, the results that you may obtain from here, they are normally similar to what you get from experiments on ductile materials, on condition that the elastic limit stress for simple tension, or rather in tension, should be equal to the elastic limit stress for compression. If the two stresses at elastic limit are the same, then we can apply this theory. And applying this theory, we'll find that the experiments we are going to get for ductile materials will give us more accurate results. But then if this condition is not met, as long as this is not equal to that, then we cannot use this theory. It may not be applicable. Then also, if you're talking about getting the results, we're saying that the results that we are getting, they are not exact, but similar to what you obtain from experiments. The problem is that you don't get the exact results that are obtained from experiments on ductile materials. So if you want something more accurate, this is not a theory you may need to go for. You may need to pick a different option altogether. Then we also have what is known as the shear strain energy theory. This is yet another theory. The first one was just strain energy theory. But in this case, we go back to something related to shear stress and strain. So we're talking about shear strain energy theory. Now with this one, we're saying that when does failure occur? Only when that strain energy per unit volume in that material reaches the strain energy at elastic limit in simple tension. So if the shear strain energy per unit volume reaches that value or close to the value at the elastic limit in simple tension, then we are saying that in material is going to fail. And of course, just like the other one, we have an expression because this is also a three-dimensional stress system. A three-dimensional stress system. So what do we have? Here we have, again, you can notice something interesting. We are introducing letter C representing a constant. We're saying the strain energy, that's why we're using U and S. U and S. You can forget about the US like the United States. This is U representing strain energy, the energy. S, strain. This is our strain, shear strain energy. So with this, we're saying US is equal to US and take a small s there, 1 over 12C, then open brackets, stress 1 minus stress 2 squared plus stress 2 minus stress 3 squared plus stress 3 minus stress 1 also squared. Now, what you are putting in the brackets, don't worry about the sequence, as long as between the three stresses, they subtract each other. If you swap, you have stress 3 minus stress 2. The results will be the same because we are squaring the result. Because you've squared it, it means even if it was to be negative, what you get will not be affected. Moving on, C is basically a constant. So here we're saying that at the elastic limit, we only have one principal stress, which is this strain at elastic limit for a material loaded in tension. So stress ET. Then what happens to the strain energy, the shear strain energy per unit volume? So here, we're going to introduce U subscript S is equal to 1 over 12C. Now, one thing you remember is that this stress 2 and stress 3 are out. And the maximum stress, which is stress 1, the tensile one, is the one that we're picking as stress ET. Meaning the other two, this one and this one, are zeroed. So if you go back to the expression and do that, you put 0 there, put 0 there, and put the 0 there, put 0. But in place of stress 1, you put stress ET. The expression becomes like that, stress ET minus 0 in the bracket squared plus 0 minus 0 squared plus 0 minus stress ET squared. The square brackets are still there also. And then outside we have 1 over 12C. On the other side of the equal sign, it's 1 U subscript S, talking about the modified now shear strain energy. Here, when we get rid of all this, you will notice that this is negative and is squared. So when you square it, it will become positive. So it is going to have a case where you add this to that. So you have 2 stress ET squared. Then you still have 1 over 12C. Here, we are not going to stress ourselves and start saying this divided by that. Not at all. Because we'll need to use this in this format in the next step. Now, so all we are doing is equate the two energies, the shear strain energy and the subscript shear strain energy, the initial expression we had and the last expression that we've just found. When we do that, you'll notice this is what we got. And at the same time, we remember that this is what we started with. I mean, this is the full expression of what we started with. 1 over 12C, then stress 1 minus stress 2 squared, then stress 2 minus stress 3, in the brackets squared, plus again stress 3 minus stress 1, in the brackets also squared. Outside all these brackets, you can already see there's 1 over 12C. The same thing on the other side, you have 1 over 12C, 2 stress squared, stress ET squared. Now this is where I said, when you notice this and this, they are the same. That's why we didn't simplify that other one. So we can cancel them out. Having done that, we again open the brackets, and this is what we have. We have stress 1 minus stress 2 squared, then stress 2 minus stress 3 also squared, and then stress 3 minus stress 1 outside the brackets squared is equal to 2 stress ET squared. That is the full expression we end up with there. Now, with this expression, you can already notice that we have 2. We were equating these, and we've simplified that, and we are now here with this further. Now, the only thing is that where we have stress T for simple tension, we can use the stress ET, we can put stress T, which is the safe working stress for a material loaded in tension, and then the expression remains the way it is. So Here we've already said, in this case, it gives excellent results where these two stresses are the same. The elastic limit stress for tension and the elastic limit stress for compression, if they are the same, then we get good results. So then, just like the other one, if these two are not equal, then you will not get accurate results. They will not be the results won't be impressive. Then also, if stress it is 0, here we're saying that the theory gives stress it is equal to 0 for hydrostatic pressure or tension. This is like an error. So this is one of the things to note when you're working with this theory. Just like the others, you notice that we're also trying to make sure that you find the facts that work with that theory. In this case, this is how things work out when you want to apply this theory also. So again, it's very good for ductile materials. Even under a variety of loads, you can use it. Let's look at an example. So here we have a shaft subjected to a maximum torque of 10 kilonewton meters and a bending moment 8 kilonewton meters at a particular section. Then this stress, let me just read it in full. The question says, a shaft is subjected to a maximum torque of 10 kilonewton meters and a maximum bending moment of 8 kilonewton meters at a particular section. If the allowable equivalent stress in simple tension is 162 megapascals, and 1 over m, that constant, is equal to 0.24. Calculate the diameter of the shaft using the strain energy theory. So remember, we've talked about two theories. We have the strain energy theory and the shear strain energy theory. This question is specifically asking us to find the diameter using the initial theory, which is the one we had started with in our discussion, which is the strain energy theory. With that in mind, let's just recollect information in the question. First, we have the torque. If you check our torque, it's written as 10 kilo Newton meters. When you see a kilonewton meter, that kilo needs to be repaired. So kilo represents 1,000 or 10 power 3. Kilo represents 1,000 or basically 10 power 3. So that being the case, it means we can now just say this T is 10,000 Newton meters. Next, you can see there is 8 kilonewton meters. This is for the moment. Again, the kilo represents 1,000. So 8 times 1,000, you get 8,000. So our moment is 8,000. That's not all. We have the tensile stress. It is 162 by 10 power 6. 162 megapascals. Again, if you check our conversion, we say a mega represents 1 million or 10 raised to power 6. Hence, our conversion you are seeing here. That's 162 by 10 raised to power 6. Of course, we also have our 1 over m, which is 0.24. So let me just take it back. Okay. So this is the information we're given. Then we will not forget we also have 1 over m, which is 0.24. Come to it sooner. Now, here we need to proceed with the working. This is a combination of moments as well as torque. With such a combination, for us to get those principal stresses, we'll need to take our equation through this expression. we need to take our equation, our analysis through this formula, which is stress is equal to 16 over pi d cubed, then open brackets m plus or minus under the root of m squared plus t squared. Now we can already see with plus or minus, it means we're going to have two results, giving us the two stresses that we're going to find. Let's proceed. Let's try to add the values and see where this will take us. So stress 1 is the one which is going to use plus because it's going to be positive and hence it's even a tensile stress. So 16 over pi d cubed, then we have m plus m squared plus t squared in the brackets and under the root. Now remember we said stress 2 is 0. Stress 3, which is the compressive one, is the one which is using a minus. So we have 16 over pi d cubed, then open brackets, we have m minus under the root of m squared plus t squared, then we close the brackets. Now again, according to the shear strain energy theory, this is where we're saying that we had stress ET there, but we've replaced it with the working stress. We said stress T is equal to stress 1 plus stress 2 plus stress 3 minus 2 over m. Then in the brackets, we have stress 1, stress 2 plus stress 2, stress 3 plus the product of stress 1 and stress 3. This is according to the shear strain, or rather the strain energy theory. And since we've already said stress 2 is 0, it already partially makes our work easier. Then we proceed to stress T squared. Stress T squared is equal to stress 1 squared plus stress 3 squared minus 2 over m, stress 1, stress 3. So next, we are going to substitute. Where we have stress 1, we will put this value, or rather this expression here. Stress 1 is this whole thing here. Stress 1 is this, which is 16 over pi d cubed, then open brackets m plus m squared plus t squared. Stress 2, 0. Stress number 3, that's where we're putting, where there is minus, where there is plus, we just change, we put minus, and we leave it like that. So what we are now doing is basically just to substitute there and get to the working. Where there is stress 1, we put this, we put there. Stress 2, we also put it there. Stress 3, we also substitute there. And then we go ahead and simplify. So that is our task. So here we are. Stress 1 plus stress 3. Because we've already established that stress number 2 is 0, then it means right from the start, we eliminate this. Where the stress 2, we've eliminated, and that's what we will basically end up with. And it's 0, so meaning even this, all that goes away. And the expression hence has become what you're seeing here. Stress 1 plus stress 3 squared minus 2 over m stress 1 stress 3. So our task now is to substitute here for stress 1 and there for stress 3. Stress 1, we said it is 16 divided by pi d cubed. Then in the brackets, I have m plus square root of m squared plus t squared. Now remember, stress 1 was carrying power 2. And everything we've written here is representing stress 1. So hence, that is squared. What about stress number 3? Stress number 3 is the same thing, except where we have plus, we put minus. So we repeat, 16 over pi d cubed, open brackets, I have m minus under the root of m squared plus t squared. And again, we said, if you check where we are coming from, this stress 3 is already carrying a square, it's power 2. So again, we do the same thing. We raise it to power 2. We proceed. The next thing I see here is that we have minus. According to this, there's a subtraction there. So this is minus. There's 2 over m. Then what do I have next? It's stress 1. Stress 1 is this expression we've written here, carrying a plus in between. So I have 16 over pi d cubed, m plus under the root of m squared plus t squared. What's the brackets? Then what about stress 3? This is the one we're saying, instead of plus, we have a minus, and this is the one we also have here. So we write it 16 over pi d cubed, then open brackets, m minus the same under the root of m squared plus t squared. This one does not carry any power because these two are just multiplying. They are not raised to any power. So we just substitute them the way they are. And the 2 over m standing on the side just like that. It's 2 over m, then the culprits are there. The next thing we do is to try to simplify. First, stress t squared remains like that. Now what am I going to do? When you say this is the first thing I can see is that 16 over pi d cubed. 16 over pi d cubed is actually common. Here I have 16 over pi d cubed. Again, here I also have 16 over pi d cubed. Everywhere I look, that's what I have. So what am I supposed to do? What are we supposed to do? It's simply to have it factorized. To have it factorized from the expression. So we are going to factor it out. So that's the one. We leave it there. Then I have m plus. Then we start now the multiplication. So what are we going to do? We will try now to multiply each of them. And because of that multiplication, you will notice if we had decided to expand, you could have seen that the square is outside there. And then it's going inside. The square is outside. There you have it. Square is outside, just like that. So with that, you can already see it's, with such, you're going to see that the multiplication of those will double also. Because this is 16 over pi d cubed over 16 pi d cubed is squared. Representing this square belongs to them. This square also belongs to this. So that's why here when we factorize, we're not just factorizing a number without a square. We're respecting that square because this alone is carrying a square and it's outside the drama of the brackets. So we factorize 16 over pi d cubed squared because that's what it is. Here it is squared because of that. Here it is also squared because of that. Here the square is coming because this one and this one, they belong to one big bracket where you can multiply this by that. So in the end, the square still is respected. So we get rid of it, so we make our work easier. Now, when we do that, when we get rid of it, then we just expand this. Expanding this means I write this twice. I write this twice. So what am I doing? I'm going to write m plus under the root of m squared plus t squared, brackets. Again, open brackets, m plus under the root of m squared plus t squared. I close the brackets. This operation I've done here, has gotten rid of this square. And having done that, I can do the same for the next one, which is carrying a minus. So m minus under the root of m squared plus t squared, everything in the brackets, open brackets again, m minus under the root of m squared plus t squared, brackets. Then we do the squares, the square brackets there, closing that business. Here again, this one has taken care of this one. So what are we doing? You can see that this whole thing here, we've managed to expand. In fact, you can already, it's like this. And even here, you have your square brackets right there. And then the other side, it's just like that. We have m plus m squared plus t squared, then m minus m squared plus t squared. The 2 over m remains like that. While here, we multiply the 2 with their difference in the sign in between. So this is minus, the other one is plus. Now, this shouldn't even bother you because all we're doing is just some algebra. So the next thing I do is to do the multiplication of these variables inside. So I'll say, first of all, 16 over pi d cubed squared. I just write it down the way it was. Next, I multiply m by m. It gives me m squared. M multiplied by m, this is m squared. What about m multiplied by this, which is square root of m squared plus t squared? I have m square root of m squared plus t squared. Next, I introduce this one. Square root of m squared plus t squared multiplied by m. I get m square root of m squared plus t squared. Then again, this is the multiplying factor this time. M squared plus t squared under the root multiplied by the same m squared plus t squared. What do I get? Because I'm multiplying two variables, variables, yes, which are already under a root. It's like square root of x multiplied by square root of x. I should be able to go back to my number. If you say root 4, square root of 4, multiplied by square root of the same number again, square root of the same variable being represented, the same 4. What you will notice is that this will just cancel out because we're now multiplying. And your result will be a mere 4. In cancelling out, you ignore 1 and maintain one of these numbers. Because square root of 4 is 2. 2 times 2, that's what you have. So you get rid of these brackets and just pick one of the numbers. That's your answer. The same thing we're doing here. When you say m squared, the square root of m squared plus t squared multiplied by the same thing, which is square root of m squared plus t squared, your result is just what is inside the brackets there. So hence, m squared plus t squared. Then when we come to this one, we're doing the same thing. M multiplied by m, that's m squared. M multiplied by negative square root of m squared plus t squared. It will still carry a negative, then m square root of m squared plus t squared. The next thing I do is bring this one, negative under the root of m squared plus t squared multiplied by m. I have again m, negative m square root of m squared d plus t squared. Then negative m squared plus t squared multiplied by the same thing, negative m squared plus t squared. This is where I was saying what is inside the brackets is the answer. So hence, our result here is simply m squared plus t squared. Then I go to the last one. I have, first of all, 2 over m here. This is 2 over m. So I've written it here, 2 over m, and we have a minus. Then inside the brackets, we are multiplying. There is m multiplied by m. I get m squared. Then next, I have, sorry, where? M, yeah, sorry, you're saying m multiplied by m, I have m squared. Then I proceed again and say m multiplied by this. It will give me the same thing, which is m outside the brackets, then m squared plus t squared. And unfortunately, it's going to be negative. Then I go back and bring out this m squared plus t squared multiplied by this, which is m squared plus t squared. So again, it will be like that. This will come out in that format. It will be m squared plus t squared. Now, you can already notice that in between, we've attempted almost to ignore one of the factors. The reason is very simple. If you notice what I have here, you can see that I have this m square root of m squared plus t squared. There's also m square root of m squared plus t squared. This plus this, it's a 2. Again, here I have negative m square root of that, another negative m. So these, forget about the brackets now, we've gotten rid of them. You will notice that this can easily cancel with that, because this is plus, this is minus. Everything else is the same. It's like 1 minus 1. The same way this can also cancel with that. That's how we've done it even with the last one, except here, I just decided to go the faster route to the C. So with that, it means in the brackets, I'll just remain with this, that, and the first one. So let me take you to where the results are cooking. Oh, here we are. So here, I've just taken a further step where I've added this to this. Then I have 2 m squared plus t squared plus that. Then I have negative 2 square root of m squared plus t squared. Everything else remains the same. And I also have, you can already see this is m squared. This is also m squared. I add them. I have 2m squared. Then again, you will see the same thing happening. I have m squared here. There's another m squared there. And again, you will see we will be able to simplify them further. This starts again, 16 over pi d cubed squared. Then I have 2m squared plus, there's a 2 here. Then there's a square root of m squared plus t squared, because these are 2. Then I also have plus t squared again. Then I also have 2m here. And I think here is just what you call this plus that. There's an m in front there, because we're trying to make it simpler. So there's m right there and m. But the beauty is that this factor here and that factor, they are going away. And how do they disappear? They will become like this. You just have 16 over pi d cubed squared, then 4m squared plus t squared, 2t squared, then everything in the brackets minus 2 over m. Then here I have m squared minus m squared minus t squared. Let's see. What if we proceed from there? This m squared minus m squared, the whole of it will cancel. It will go. It's like, again, 1 minus 1. Then here, everything remains the same. 16 over pi d cubed, then square outside. Inside the brackets, I have 4m squared plus 2t squared. Then 2 over m, then there's a t squared outside there. Now with this, I can already see that 16 over by d cubed is okay, it remains like that. But if I look at this expression, which is 4m squared plus 2t squared, it can be on one side. I can decide to simplify it, where I factorize it, but then I put a small one whereby if I multiply, if I take this back, everything should still go back to where we were. In other words, if you look at this, I'll have this expression coming there, and there will also be 2 over m. There's a t squared over there. Nothing is going to be changed. Everything will just be the same. So here, there's 4m squared plus 2t squared, then 2 over m, then there's a t squared there. So then the whole of it simplifies to 1 plus 1 over m. Then we've maintained what is on the other side. Then we can now proceed. With this, we want the square root. Introduce square roots on both sides because we want the stress t to be alone like that. So everything else here is under the root, but 16 over that squared, it cancels with the square root, so it remains the normal number like that. We can now substitute. Our substitution is 162 by 10 power 6 is equal to 16 over pi d cubed. Then open brackets are 4 times 8,000 plus 2 times 10,000 plus 1 plus 0.24. 0.24 is 1 over m. T is 10,000. Your m is 8,000. We don't know what d is. And then this is 162 times 10 raised to power 3. Now, from there, you can make d the subject, and your answer is 0.089, which is, if you convert this to millimeters, it becomes 89 millimeters. So the question you may be answering, trying to answer is, why do we have to go through all this? Why not take the question from here? Let me take you back. Yeah, just from here. Yeah, right from here. Because we already have the stresses, name them, so you can just say stress is equal to. Yeah, so here you notice that already it's m plus or minus. When you start that and you do the replacements, your expression becomes longer and more complicated, and it's easier to make those mistakes. But after you simplify it, you take it down to where we are, you go straight to your final answer without a lot of problems, just like that. So this is the expression that we use, and then we are there. D 0.089. So I've also given you 2 questions for the exercise, planted the answers there as well. Take your time to go through. Like we always say, reach out in case you have something that needs clarity in what we've put up here, or you can always drop a comment in the comment section.